Good morning students. Welcome back to session 9 of Hilbert spaces class. So in this class let us study the projections on Banach spaces and Hilbert spaces and also a perpendicular, what is meant by a perpendicular projection and results based on these concepts. First let us begin with the definition of a projection on a Banach space. A projection on a Banach space is an idempotent operator on B. A projection on a Banach space is an idempotent operator on B. In other words, E is a projection on B if and only if E square is equal to E. Okay, this is the definition for S idempotent operator and E is continuous. So a projection on a Banach space is an idempotent operator on B. Okay, so to have a map E defined on the Banach space B to be a projection is, so it is idempotent as well as it is continuous. Okay, let us take up this theorem. Suppose P is a projection on a Banach space B. Suppose P is a projection on a Banach space B. And let M and N be its range space and null spaces respectively. Okay, then M and N are closed linear subspaces of B such that B is the direct sum of M and N. Okay, we need to show the range and null spaces of the projection P is closed as well as B is the direct sum of M and N. Okay. Now, by definition, P is a projection on a Banach space means P square is equal to P and P is continuous. Okay. Now, we show M and N are closed subspaces of P. Now, by definition of a null space, N is the null space means what? N is equal to set of all x belongs to B such that P of x is equal to 0 means it contains those vectors of B which are mapped onto the 0 element of 0 vector of SB itself, because P is a mapping from B to B. So this is nothing but what? Inverse image of the singleton set 0, because so inverse of these will be definitely contained in N. Now look here, P is continuous. P is operator means it is a linear operator means it is continuous. Now P is continuous and 0 singleton set 0 is closed. Inverse image of a closed set under a continuous map is also closed, means P inverse of 0 is closed. P inverse of 0 is closed subspace of B, but P inverse of 0 is N, therefore N is a closed subspace of B. Understand now? So N is a closed subspace of B. Similarly, M is the range space. M is the range space means by definition M is equal to set of all x belongs to B such that P of x is equal to x. Okay. This is equal to set of all x belongs to B such that this can be written as I minus P of x, because x can be written as I of x. So I minus P of x is equal to 0. Now set of all x belongs to B, I minus P of x is equal to 0 means this set is the null space of the operator I minus P. So this is the null space of the operator I minus P. Now the identity map I is continuous, P is continuous means sum of two continuous functions is continuous, therefore I minus P is continuous. And again as 0, and this is nothing but the inverse of, this is nothing but this is the set, nothing I minus P whole inverse of the singleton set 0. So this is nothing but the inverse image of I minus P inverse of 0. Now as I minus P is continuous, 0 is a closed set, therefore I minus P inverse of 0 is closed, that means M is also closed. Now the null space N is closed, the range space M is also closed. So what you have to show here, M and N are closed linear subspaces of B. Now we need to show B is the direct sum of these subspaces. B is equal to M plus N. This we already proved in the previous class itself. Okay. So we have shown that if M and N are null spaces of a Hilbert space H, then H is equal to M plus N itself. Okay. Now look here. Now if our space is a Hilbert space instead of a Banach space P, then we single out those projections on H whose range and null spaces are orthogonal. Okay. So instead of a Banach space, our space is a Hilbert space. Then what we do is we delete, single out means we delete those projections on H, or we take up those projections on H whose range and null spaces are orthogonal. Such projections are called perpendicular projections on H. Okay. So since we have taken the Hilbert space H, we can definitely define what is the orthogonality here. So we will take those S projections whose range space and null spaces are orthogonal. That type of projections only we will consider it on the Hilbert space H. Those projections are called the perpendicular projections. That is, a projection P on a Hilbert space H is said to be a perpendicular projection on H if the range M and the null space N of P are orthogonal. Okay. So projection is called a perpendicular projections if its range and null spaces are orthogonal. So let us prove this theorem now. If P is a projection on a Hilbert space H with range space M and null space M, then M is orthogonal to N if and only if P is self-adjoint. P is self-adjoint means what? P is equal to P star. P is equal to P star, and in this case N is nothing but the orthogonal complement of M. N is equal to M perp, means N is the orthogonal complement of M. Okay, understand now? Or in other words, a projection P on a Hilbert space H is a perpendicular projection if and only if P is self-adjoint. P is self-adjoint. Let us prove this now. First, suppose P is a projection on a Hilbert space H with range M and null space N. Then by definition what will happen? Just now we have proved then H is the direct sum of M and N. Okay. First we show M is orthogonal to N. First suppose M is orthogonal to N, and we will show that P is self-adjoint. Okay. Now M is orthogonal to N. Now you take Z belongs to H be any arbitrary point. Then since H is the direct sum of M and N, then this point Z belongs to H can be written as Z is equal to X plus Y, where X is an element of M and Y is an element of N. Okay. So now you consider inner product of P of Z comma Z. Inner product of P of Z comma Z. Now inner product of P of Z comma Z means P of Z is, P is a projection means P of Z is what? X. Because M is the range space. So X belongs to, look here, X belongs to M means what? X belongs to M means P of X belongs to M means what? P of Z is X comma Z, that's equal to X comma Z means X plus Y. So this is equal to inner product of X comma X plus inner product of X comma Y. Now X belongs to M, Y belongs to N, and M and N are orthogonal means inner product of X, Y is 0. Therefore this will be equal to only X comma X. Also P star of Z comma Z is Z comma P of Z, that's equal to Z comma P of Z is again X. So Z in place of Z I can write X plus Y comma X. This is equal to X comma X plus Y comma X. Again X is orthogonal to Y means Y is also orthogonal to X. Therefore inner product of Y comma X is 0. This implies we leave at only inner product of X comma X. Now inner product of P of Z comma Z is also X comma X, and inner product of P star of Z comma Z is also X comma X. Inner product of X comma X. Therefore you can declare that inner product of P of Z comma Z is equal to P star of Z comma Z for every Z belongs to H. This implies what? You transform the right hand side term to left hand side. This becomes p minus p star of z comma z under inner product is equal to 0. So now you know that inner product of t of x comma x is 0 implies t itself is 0. Accordingly, p minus p star is 0. P minus p star is 0 means what? P is equal to p star. P is equal to p star implies that P is a self-adjoint operator. So we have assumed that M is orthogonal to N and we have shown that P is self-adjoint. So conversely, suppose that P is self-adjoint. Then we need to show, yes, conversely suppose that P is self-adjoint and we will show that M is orthogonal to N. Suppose x belongs to N and y belongs to N are arbitrary points. Then inner product of x comma y is equal to inner product of x means I can write p of x comma y because M is the range space means what? P of x is equal to x itself. So this is equal to p of x comma y, that's equal to x comma p star of y. So p transferred to right hand second term. So this is equal to x comma, since p is self-adjoint, p star is same as p, therefore x comma p of y. Now y belongs to null space of p means what? P of y is 0. So inner product of x comma 0, that will be equal to 0. Therefore the inner product of x comma y is 0, where x is a point vector of M and y is a vector of N. Therefore these two are arbitrary means for every point this holds true, means M is orthogonal to N. We have shown that M is orthogonal to N. Now we have to show what? We have to show that N is nothing but the orthogonal complement of M. That is, we have to show N is equal to M perp. So for this, let x belongs to N. Then x belongs to N means what will happen? Then as M is orthogonal to N, x is orthogonal to M. X is orthogonal to M means what? X belongs to M perp, orthogonal complement of M. Therefore, what will happen? X belongs to N implies x belongs to M perp implies N is contained in M perp. Okay. Now we have to show that M perp is contained in N. Okay. For this, suppose on the contrary, assume that N contained in M perp properly, means the reverse is not true. Then what will happen? N is contained in M perp properly means then N becomes a closed, because N is already closed, because M and N are closed linear subspaces. Now N is a closed proper subspace of a Hilbert space M perp. Okay, because subspace of a Hilbert space is also a Hilbert space. M perp is closed subspace, therefore N is a closed proper subspace of a Hilbert space M perp. But we know that result, if M is a closed proper subspace of a Hilbert space H, then there exists a non-zero vector, say Z0 belongs to H, such that Z0 is orthogonal to M. This result we have proved in the previous classes. Therefore, by the above result stated, so there exists a non-zero vector Z0 belongs to M perp, okay, such that Z0 is orthogonal to N. Now, Z0 belongs to M perp implies what? Z0 is orthogonal to M. Now, Z0 is orthogonal to M as well as Z0 is orthogonal to N means Z0 is orthogonal, which is the vector which is orthogonal to both the subspaces. That vector is nothing but 0 vector. That means Z0 is equal to 0, which is a contradiction to this result because Z0 should be non-zero. Why this contradiction arises? Due to assumption that N is contained in M perp properly. So this is a contradiction, means M perp is also contained in N. Now N is contained in M perp and M perp is contained in N means N is equal to M perp. Okay. Thus we have proved the theorem. Now look here. In the theory of Hilbert spaces, we shall always consider those projections which are only perpendicular, as I said. Therefore, for the sake of convenience, we can omit the repeated use of the word perpendicular. Means whenever we have a projections on a Hilbert space means they are the perpendicular projections, or when we say it's a perpendicular projections means this is simply a projection means, so thus a projection P on a Hilbert space H we shall always means a perpendicular projection. We will not use the word perpendicular projection every time. Only we just use P is a projection on Hilbert space, then it is understood that it is a perpendicular projection. Therefore we define an operator P on a Hilbert space H is projection if and only if, what is the condition? First one is P should be idempotent, P square is equal to P, and P is self-adjoint, P star is equal to P. Clearly the zero operator and the identity operator are clearly projections on H, because 0 square is 0 and 0 star is 0, I square is I and I star is also I star. So I star is also I. If P is a projection on Hilbert space H with range M, then we know that M is a closed linear subspace of H. This we have proved. And also if N is a null space of P, then also N is a closed subspace of H. And N is nothing but, just now we have proved, N is nothing but the orthogonal complement of M. Okay. Further, if M is any closed linear subspace of H, then we know that we have proved H is the direct sum of M plus M perp. Therefore, there is a projection P on H. Therefore, there is a projection P on H with range M. This projection P is defined by P of Z, that is P of Z is equal to P of X plus Y is equal to X, where X belongs to M, Y belongs to M perp. Thus, in the case of Hilbert space, there is a, what will happen? There is a one-to-one correspondence between the projections on a Hilbert space H and closed linear subspaces of H. Projection on a Hilbert space and closed linear subspaces of H means whenever we have a projections on H, definitely some range space exists, that is M exists, M become a closed linear subspace. Okay, and also when M is a closed linear subspace, definitely a projection exists on H, because M exists means M perp also exists. Therefore, we can define a projection on M with range M and null space M perp. Okay. Therefore, I will state this remark. If P is a projection on a Hilbert space H with range M and null space P is if P is a projection on a Hilbert space with range M, then the null space of P can be uniquely determined and is always M perp. Means this is a only one. It is uniquely determined and that is M perp only. Thus, there will be only one projection on H with range M. So, therefore, instead of saying P is a projection with range M, we simply say P is a projection on M. So, instead of saying P is a projection with range M, so we shall say that P is a projection on M. So, in the next theorems, whenever we say P is a projection on M, it is understood that M is the range of P. Okay, M is the range of P. So, next one, say, suppose P is a projection on a closed linear subspace M of a Hilbert space H. Okay, P is a projection on a closed linear subspace M of a Hilbert space H. Then this happens if and only if I minus P is a projection on M perp. Means if P is a projection on M, then I minus P is a projection on M perp. Its orthogonal complement. First, suppose P is a projection on H. P is a projection on H. P is a projection on H means what? P square is same as P, means P is idempotent and P star is equal to P. Now consider I minus P whole square. I minus P whole square is I minus P into I minus P, that's equal to I minus P into P square. The P square means P itself. P is, because P is idempotent. So this is equal to I minus P plus P. So these two get cancelled. We get I minus P only. Therefore, I minus P whole square is equal to I minus P. Let's check the second condition. And I minus P whole star is what? I star minus P star. This is equal to because I star is I and P star is also P. Therefore I minus P means I minus P whole star is I minus P whole square is I minus P. Therefore we can declare that I minus P is a projection. I minus P is a projection. Now we show that if M is the range of P, then what will M perp is the range of I minus P. We show that if M is the range of P, then M perp is the range of I minus P. Suppose N is the range of I minus P. Okay, I denote the range of P by N. Then X belongs to N implies, by definition of a range, I minus P of X is what? X itself. This implies X minus P of X is equal to X. X get cancelled, therefore P of X is equal to 0. Now P of X is equal to 0 imply what? X belongs to null space of P. What is the null space of P? Null space of P is nothing but M perp, means X belongs to M perp. Now we have taken N is equal to X belongs to N and we have shown that X belongs to M perp. Therefore N is contained in M perp. N is contained in M perp. What is N? N is nothing but we have assumed that N is the range of I minus P. So now let us take up the converse part. Say conversely, let X belongs to M perp. X belongs to M perp implies what? P of, because M perp is the null space of P. Null space of P means what? P of X is equal to 0. This implies I add and subtract X. So this gives X minus P of X is equal to X. So this implies I minus P of X is equal to X. I minus P of X is equal to X means what? X belongs to range of I minus P. What is the range of I minus P? Range of I minus P is nothing but N. Implies X belongs to N. Therefore, X belongs to M perp implies X belongs to N. Therefore, M perp is contained in N. Now, N is contained in M perp, we have proved, and M perp is contained in N. Therefore, N is equal to M perp. Okay. So, we have shown that. So, we have shown that N is nothing but M perp. N is nothing but M perp. Thus, we have shown if P is a projection on a closed linear subspace M of H, we have assumed this, then I minus P is a projection on M perp. I minus P is a projection on M perp, because we have assumed that N is the range of P. Okay. Conversely, let I minus P be a projection on M perp. What you have to show? P is a projection on M. Okay. So now I minus P is a projection on M perp implies what? Then by the first part of the proof, what will happen? If I minus P is a projection on M perp, then I minus P. I minus P means P is a projection on M perp whole perp. That is M perp, that's nothing but M, because M is closed. Therefore, by the first part of the proof, I minus P means P is a projection on M. Therefore, P is a projection on M. So, thus we have proved that P is a projection on M if and only if I minus P is a projection on M perp. Okay, I minus P is a projection on M perp. These are the few results for this class. Thank you.